I think we'll go ahead and get started here. My name is Spence Snively. I'm a solutions architect with AWS. In this session, we're going to be covering data lakes, how to build data lakes on AWS, what a data lake means, and really some patterns and best practices that we've seen customers take when building data lakes. So how many folks in the room are familiar with data lakes already? OK, a good number. Excellent. How many of those folks are currently implementing a data lake for themselves? OK, maybe half the room or so. Really, data lakes really popular for customers to start building on AWS. And if we take a step back and we look at big data, there's different ways of defining big data. But it really boils down to a couple core tenets, or V's that the industry calls. The most common way of thinking of big data is volume, but it doesn't have to be volume-based. So you don't have to have petabytes, exabytes, that sort of size of data to have big data. Sometimes you might just have a lot of messy data. What if you have a lot of unstructured data, semi-structured data? You might have a lot of different data sets that need to be combined together. And all of those sorts of use cases actually fit into the big data space really well. So even though it says big data, you might have relatively small data, but they fit these other characteristics, and these sorts of techniques still really apply to that sort of use case. And if you really look at it, there's a couple industry reports, screenshots that we see here. It really comes down to this rapid data growth. If you really look at today's data, over 90% of today's data has really been generated in the last 2 years. So if you actually look at the rate of data being generated, it's growing very quickly. And customers, like yourselves, want to really be able to take that data and drive insights from that data. But not only that, the type of data that is being generated is different. It's a lot of IoT data, a lot of sensor data is getting generated, a lot of unstructured and semi-structured data sets from social media and other data sources. So the variety of data sets that are getting generated are constantly growing. So it's not just that rapid growth, that high volume of data, but also the types of data getting generated. So with data lakes, I won't spend a ton of time introducing what a data lake is, since a lot of the folks in the room are familiar with data lakes. But with a data lake, it's all about being able to quickly ingest your data. So if you have a data set and you want to really get it into the lake, the amount of work that is needed to be able to do that should be very seamless. It should be very easy to get the data into the data lakes. Not only that, but also different types of data. So if you have all this unstructured data, semi-structured data, even if it's structured, being able to rapidly ingest that data into the data lake is really critical so that you could get the data in there and start running tools and running analytics on that data. And the key part about running analytics is being able to really future-proof. What we mean by that is, as you get your data into your data lake, you want to be able to have a suite of tools to be able to run on that data. If it's actually stovepiped, siloed into one sort of tool, then it's really hard to start experimenting and using other tools on that data. So the architecture really needs to be able to adapt and be able to run different sorts of analytics on that data to be able to drive those insights out of that content. And of course, security. With all this data, it really needs to be very secured, controlled, audited, fine-grained access to all that other information that you, or things that you would expect, because data lakes are really fabulous at driving insights, but you also have to have them very protected at a protection layer, because it's a lot of sensitive data most often. So if we take a look at a general architecture, and we're going to dive into how to dive into each of these pieces, what the best practices of those pieces are. But if we take a look at the architecture, we really see some key components. The first in the middle is, most people think of just storage, right? Storage by itself, really great, but isn't really the only component that makes up a data lake. Another really important aspect to a data lake is cataloging of your data. Being able to understand what data you have, where is it, what does the schema look like, what is the format, how can I make it so all these different tools could really process and ingest that data. You really need to have a catalog that supports that in addition to where that data is being stored. So those two things really make up that core component. It's not just the storage and it's just not the catalog. But also you have to get the data into the data lake. So there one of the key takeaways and the things I like to talk to customers about is you don't necessarily have to use one tool for all your ingestion. The way you ingest data from a relational database into a data lake, maybe doing CDC, change capturing, is very different than the way you might capture clickstream data from your users, which is very different than the way you might capture satellite imagery. For example, Digital Globe has 100 petabytes of data that they ingested through like a snowmobile. So all the ways of ingesting your data, oftentimes is very, very specific to what type of data you have and how that data is getting generated. But the key thing is after it gets into your data lake, the way it got into your data lake doesn't really matter as much. So you might have different data sets coming in, and one data set might be use one method of getting it into the lake, while another data set might be coming in through a different means. And then, of course, the analytics, the driving insights. Data lakes are really great at powering analytics, machine learning, that sort of capability on top of it. And you'll notice this is drawn as decoupled, right? So what that means is the way you get your data in doesn't influence and isn't really dependent on the way you store it, which isn't really as dependent on the way you analyze it. So having that decoupled architecture is another way that you actually future-proof. And you can also start small that way. So patterns and some lessons learned and some things to think about as you're looking at your data lakes. The first thing is, what data do I have? Storing your data in a data lake, in S3, for example, and not being able to know where the data is, what the format is, it's almost like you don't have it there anymore, right? You really have to know where your data is to be able to process, analyze, drive insights from it. Gartner has two nice quotes that I like to steal a lot of times. The first is, in 2018, 80% of the data lakes are going to be ineffective because of poor metadata management. What they're trying to elevate here is the importance of being able to have that catalog and good metadata management on your data lake. The other quote that I kind of like is really taking that data lake analogy another step is the fish finder. It's letting you find your data that you care about for that particular type of analytic. So there's a couple of ways of doing your metadata management on AWS. One of the first ones we're going to talk about is using the Glue data catalog. How many folks are familiar with Glue already? Okay, maybe a third of the room. So Glue has two key components to it. One of them is the ETL portion that allows you to run serverless ETL through either PySpark, Scala Spark to be able to run transform loads. The other is the data catalog, and these things could be used together, or they might be used separately. For example, Dow Jones presented at the New York Summit a few weeks ago how they're heavily using the Glue data catalog, but they're using things like EMR to do their ETL versus using Glue. So you don't have to use the entire suite, even though they're very, very nicely integrated together. So this data catalog is Hive compliant. Why you care about that, why I want to mention that is, in order to have a lot of different tools to be able to process and understand the data, it first has to look up what data do I have and where does it live. And having it Hive compliant, that's one of the de facto standards ways of defining metadata stores on premises that people are running on Hadoop platforms. Having that allows it so it's very easy to integrate with Hadoop-style analytics. But it doesn't have to be. You could run within SageMaker and query your data catalog and do TensorFlow, MXNet, Caffe, the different types of machine learning algorithms or deep learning algorithms on your data as well. The other really important aspect is what really makes a metadata store or a data catalog very, very effective is not necessarily populating it once and forgetting about it, because your data sets change, your formats might change. Being able to really have that data and have a way of governing or maintaining that data set over time. And that's really where these crawlers come in. Crawlers aren't the only way of doing this. We'll talk about a few other ways. But crawlers are really great if you don't know which data sets are in your data lake. So let's say you may know a little bit about the data set, but you don't know the field names, you don't know the variable names, those sorts of things. What these crawlers allow you to do is it allows you to really plug it into your data lake or your relational databases, your data warehouses. Usually you know the schemas of those because they're schema on right. But essentially what you can do is point it to those data sets, and these crawlers will look at the actual data. and derive, oh, this is a JSON data, this is XML, this is a CSV, this is Parquet. And then as it's deriving that information, it will be looking at the fields and give you all the different fields you have, along with what the data type is of those various fields. So one example is, a lot of times I like to give demonstrations processing New York City taxi data. It's about 8 years of data. It's about 3 billion entries. Nice public data set to play around with. And what's interesting is, when you're actually crawling that data set and analyzing it and looking at it, you could actually use these crawlers to be able to derive all the different fields. And even though it's CSV data, and CSV data is naturally all ASCII, right? There's no data types in a CSV file. It derives, oh, this is a longitude, it needs to be a double. This is a date, these are the different fields. So even though the data source itself doesn't define those fields all the time, these crawlers will actually discover those for you. The crawlers do great, but they're not perfect all the time, right? They're an automated process to be able to discover these schemas. So if you actually crawl it on a data set and you have a lot of optional fields, and you don't have all the fields in the data set that it crawls, you might actually have new data come in and it has new fields because it's very sparsely populated, as one example. Or maybe it found a data set, for example, the flight data, it saw a flight number, it treats it as a string, but maybe you want to treat it, or it found it as an integer, but maybe you want to treat it as a string because there's no numeric, you don't want to average flight numbers for a certain carrier, right? It's more of a string field. So what you could do after it populates your catalog is you could go in there and modify the different data types or add fields, that sort of thing. So these crawlers are really, really great at being able to populate your data set, but you could run them over time as well. So as your data is changing, it could discover that as new partitions come into your data lake, it'll discover those partitions to be able to maintain all that information there. It's interesting. I was working with one customer that had a very, very unique log format. It was some telco equipment. It was emitting a very, very interesting log format that wasn't really CSV. It wasn't tab. It had like all these parentheses with different units, that sort of thing. And they wanted to be able to use Glue. They wanted to use these things. And that's where these custom classifiers come in. So these custom classifiers really allow you to define your own rules of processing your data. And those come in different forms. So if I have data sets, and one record is always separated by a new line, but the way that's encoded is very, very unique. What you could do is you could use a Grok format. What Grok will do, it's an extension on top of regex that has these patterns built into it. And what you could do is you could say, oh, here's an IP address. There might be a dash here. Here's a date. Here's a comma. And then here's some more fields. Where the delimiters might be very, very unique as you're processing the line. But you could define that expression in that Grok formula. And then what the crawlers will do is they'll actually use that to discover all the data. And then really, really nice aspect of all this is that gets abstracted away in your catalog. So as you use tools to be able to analyze your data, maybe it's using SQL-based queries on top of your data using Athena, or maybe you're bringing it in on EMR, or using various tools on top of it. That custom format is actually abstracted away from the people writing the analytics. So each person doesn't have to figure out what that regex or that Grok format is, that Grok expression. It's actually in the catalog with the right SERDI, and then they could use those tools on top of it so that they just see the logical view, not necessarily the concrete mess of whatever log format that was. So really, really great to be able to do that and bring your data sets in. We have XML and JSON classifiers as well to be able to pull out the different fields of those data sets and be able to process that. So some other ways of populating your catalog, and then we're going to start going through the ecosystem. So right now we're talking about cataloging, but we're going to talk about ingestion, analytics, machine learning. So we're really going to step on all these aspects. We're not going to just talk about necessarily just one part of the data lake. But there's other ways of populating your catalog. So let's say you're actually running a Hive metadata store, maybe on RDS or maybe on premises, that sort of thing. What you could do is you could actually use import-export scripts. So you could take your Hive metadata store. You could run these scripts and populate the Glue data catalog. Or if you want to go the other way, you could take the Glue data catalog and populate your Hive metadata stores. So if you're doing a migration, maybe from on-premises, you could actually both migrate your HDFS data through HDFS endpoints through S3, through Snowball. as well as you can migrate the Hive metadata stores, that sort of thing, using a lot of these techniques. There's some really good talks about just migrating Hadoop workloads. Hour-long talks just focused on that. Some really good patterns if that's what you're looking at doing. So metadata management. What about how to get the data into your lake? And this is really where it's a pretty common theme, but this is really where it's important to use the right tool for the right job. So if I have, for example, if I'm using Kinesis or Kafka, and I'm trying to do streaming data and populate my data lake, if I try to start sending like all these big images over that, or all these other large data sets, it becomes very, very messy to manage. It's a lot of times it's a lot better to use different ingestion techniques for the different data sets and how those data sets are getting generated. So if we take a look at some of these, on the real-time flow, definitely IoT Core has some really good adapters to be able to take IoT data coming from MQTT or coming through WebSockets and different channels and getting that into Lake or Kinesis. We're really going to talk about Kinesis in more depth here. So Kinesis, really, really great at being able to handle streaming data. So this could be the IoT data coming from IoT Core. It could be sensors out, kind of out in the wild. However you're getting streaming data, Kinesis data streams is really, really great. You can start small with one shard. You can scale it up, scale it back down as you need to. What's really great is you could create kind of this big data Lambda architecture, a little different than AWS Lambda. But this architecture to be able to handle both real-time analytics off of your real-time feed. For example, you could do Kinesis data analytics. You could use Lambda. You could use Spark on EMR. And this flow, this top flow up here, actually is the real-time processing flow. But what's really nice is you can set up this flow and then plug it into a Kinesis Firehose to then take your data and populate your data lake with all the data as well. So you could both do the real-time analytics, kind of using the tool of your choice. There's only a list of 4 up there, just because I didn't want to clutter the slide. But you could use Flink. You could use a lot of the other tools. You could use Storm to be able to process the data off of that real-time feed. And then you could also then populate your data lake with that data. And the important part of this is with AWS, with S3, as well as if you're doing this on premises, kind of one of the big Achilles heels of data lakes is really, really small files, right? You don't want really, really small files in your data lake a lot of times because those end up adding a lot of overhead, even if it's just HDFS on premises, a lot of overhead as you're running your jobs, as you're running your analytics. This flow right here actually optimizes against that. So it really enforces the best practice because Firehose will let you take all that data, batch it up, and then store those batched objects. They could be encrypted with KMS. You could actually compress them as well, and it batches them up into the larger block sizes and writes them out. But then you can still have your real-time flows up at the top to be able to have your dashboards, that sort of thing. So Kinesis is really great at real-time data. You might be getting your data in through Kinesis. You might be getting the data in through S3 adapters. Many different ways. One of the really key takeaways that I would say is, regardless of how you're getting your data in your data lake, don't try to transform it right away. Don't try to do a whole bunch of ETL on the data as part of your ingestion flow. Really good pattern to ingest your data in the raw form. CSV, Parquet, some custom log format that's really hard to parse. Ingest the data in that form, and then we'll talk about ways of prepping that data for the various analytics. And the reason why that is a lot of times when you're dealing with these data lakes and these big data systems, it's really hard to recover from errors and recover from any issue that you might have. And if you're always storing the raw data, you always have that source of truth to go back onto. You might want to do things like set up these lifecycle policies to be able to move it to Glacier and pay 0.4 of a cent per gigabyte on your data. But always have that raw data in that data lake to be able to, even if it's in the cold part of it and you need to rehydrate it in worst case scenarios, if you don't do this and you have some ETL script that's transforming the data and then there's some error, something goes wrong in that ETL script, it's really hard to recover in a lot of these systems depending on the size of them. Kind of related to the tiered storage, there's really these different classes in S3, these different object classes. A lot of times, a lot of the data will fit in S3 standard. That's what you generally think of when you just talk S3 in general. It has the 11 nines of durability. It has very high availability, that sort of thing. What you can do is you can actually, in your lake, especially for this raw data, you can set up these lifecycle policies so that as you process your data, or maybe you say it's going to stay in hot storage for 30 days, but then I want to move it to infrequent access or cold storage, you can set up the lifecycle policy to do this automatically for you. That way you could drive your cost down, to be very, very low, 0.4 of a cent per gig per month. But then you always have that source of record to go back onto if something goes wrong. So really, really good pattern to be able to have that raw data, but have that lifecycle policy to drive those costs down. You'll notice it's a fifth or maybe a sixth of the price of kind of S3 standard, which is only 2.3 cents. But so kind of shifting back to those best practices, have that raw data sets coming in and have that immutable. What that means is if you're getting data from a database, don't necessarily update your records. Have the original record, and if that record gets updated, have another time entry saying it's almost your event journal. This record was updated with this field at this time. So it's really, really good to have, at least in the raw data set, that's all immutable. You're always appending, even if you're setting up those cold storage rules to be able to grow that truth. A lot of times that data is really interesting for data scientists to see how data changes over time, not just necessarily the most recent view of your data, but what did that data look like over time. And then, that's really, really great, but how do we optimize? How do we really make this powerful for people to run analytics, machine learning on, that sort of thing? And that's where these curated data sets. So, I mentioned Dow Jones. Dow Jones is doing this, had a really good talk at New York Summit. We have examples like FINRA. FINRA ingests 70 to 90 billion events every day of various stock trading and identifies market manipulators, people trying to do fraudulent activities on the stock markets. And very, very common pattern to have that raw staging location and that curated data set for your analytics, your machine learning, your data scientists. One of the ways of doing that is, it doesn't have to be different buckets per se. I drew them as different lists of buckets here, but having these different areas. Each of these areas might have different access controls, right? The people that have access to your raw data might be much, much finer grained or much more limited than the people that have access to the curated data sets. So as the data's coming in, it goes into this raw phase. Or raw location, and then oftentimes you want to do ELT, ETL. A lot of times people will refer this as ELT because you're actually storing the data. You're extracting it from the source, storing your data in S3 first, and then transforming it later on to create these curated data sets. In this example here, I happen to be showing Glue as that icon. I didn't really call it out. But you could use other services like EMR. We have customers that are using NiFi and other open source projects as well. But kind of architecturally, this is a really, really good pattern to be able to have your curated data sets. Those might be mutating data sets. You might actually create these materialized views where it's always the most up-to-date view of your data that these analytics are running on. So kind of going through the ecosystem, ingesting kind of that ETL, ELT pipeline, the data management, how can I start analyzing this data, start driving insights from the data? And that's really where we kind of go up the stack here and talk some about our analytics services and how to structure some of these, when to use some of these, when not to use others. For example, I get questions all the time, should I use Athena versus Redshift Spectrum, those sorts of things. So within the analytics section, one of the first things I like to ask a customer, if they say, Ben, what service should I use for this? One of the first things I like to ask is, what are you trying to solve, and who are the users, right? Who's using the system? Because who the users are and what types of problems you're solving is very, very a strong driver to the types of tools that you may want to use. For example, if you're doing data science work, data engineering, analytics, the tools that those professionals use are going to be quite different than like a standard BI user that might not be very tech savvy. All of these are powered from the data lake, but there's different flows going into the lake. But they're all using the common storage, the central S3 storage, as well as the catalog on top of that. So on the data science, and we're going to spend more time talking about how to structure data science platforms. I think we have a couple examples for FINRA, their unified data science platform, and some others here in a moment. But what you'll see here is different UIs, so SageMaker, Kibana, Zeppelin, Jupyter environments. Those are very development savvy. So I would never ask a business analyst who isn't very tech savvy to use a Jupyter notebook, right? You need to be able to write these code fragments, that sort of thing. But then you might have your business reporter, business analyst using a QuickSight, a Tableau, a MicroStrategy on top of your data warehouse. And this is a really important aspect. A lot of times people will ask, should I use a data warehouse or should I use a data lake? And you might use one or the other, but they do complement each other very, very, very well. And a lot of times, if you have an application that needs to be able to have very, very strict SLAs for business reporting, if you're using Tableau, if you're using QuickSight, MicroStrategy, these sorts of tools, and you have very, very tight SLAs on reporting, that sort of thing, a lot of folks are still leveraging the data warehouse for that, Redshift, that sort of thing. If you really have this need to be able to run advanced analytics, machine learning. It's scanning giant corpuses of documents to do different sorts of analytics on the data. That's really where we see a lot of folks leveraging the data lake directly. So let's step through a couple of these. So the first is Amazon Athena. How many folks are familiar with Amazon Athena? Okay. Maybe half, maybe a little bit more. So Athena, really good complement to your data lake. So it really provides SQL-level access into the lake. Integrates with things like the Glue data catalog. So what you could do is you could actually set up these crawlers with the custom classifiers, and then you could use Athena to be able to start querying that data through SQL. And the important aspect about this is, remember, the data actually is stored in the raw form. So that might be a JSON document, it might be a CSV, it might be whatever format it's in. What you can do with Athena is, as you're understanding your data, you might want certain users to be able to query the raw data to better understand it, maybe to populate a data warehouse or do something else with the data. What this allows you to do is it's considered schema on read. What that means is the data gets stored in S3 in the raw form, in whatever format it's in, and then the schema is actually applied, the logical table is applied as you're querying. And really nice to be able to take a data set. The New York City taxi data, a lot of times we'll demo within about a couple minutes. We bring the data in S3, we run the crawlers, and we're able to start doing select statements on the data set and analyze the data better. So it really lets you start investigating data really well. What's interesting, though, is you could also join data sets together that are in different formats. So if I have JSON data over here, I have Parquet, I have CSV, in one statement I could create a join criteria and start joining the data together. It's not going to be as performant like if you have two giant fact tables that you traditionally put in a data warehouse and you try to do like joins across that. It's not really meant for that sort of ad hoc querying today. That's really where like Redshift and Redshift Spectrum would fit in great. But really great at being able to do that ad hoc querying against your data set. The other service here that we see a ton of customers use, and we'll talk about some of the ways of structuring this in a moment, is Amazon EMR. So we're going to dive a little bit more into EMR here on the next couple slides. EMR really provides I like to say it's the Hadoop and Spark ecosystem as a service. It's not just MapReduce, it's not just HDFS. It provides, if you want to run Flink or Presto or Spark or Hive and Pig and Tez and all types of different applications. There's 19 of them right now supported on EMR. And we have ways of bootstrapping clusters. So if you have some really custom thing, I've had customers want to run like OpenTSDB, which runs on top of HBase. We provide HBase on top of EMR, but they ran bootstrap actions to load OpenTSDB, which is a open source time series database that lives on top of HBase. So it's really easy to take this platform, launch the cluster, but then extend it. It's interesting because this is actually one of the services where we do a lot of the heavy lifting of running the Hadoop and Spark for you, but you actually have direct SSH access onto the EMR cluster. A little different than things like RDS. If you think of RDS, you don't actually have SSH access onto the database. You just have that logical JDBC, ODBC access. So you have a lot of flexibility with EMR to be able to customize that Hadoop environment, even though it's considered a higher managed service. And what these environments look like, I spent, before joining AWS, been here about 3.5 years, I actually built a few on-premise Hadoop clusters. And building on-premise was always a challenge. We always did this capacity management. And one of the key concepts of on-premise Hadoop clusters is coupling storage with compute, right? When you're building a cluster, you want to figure out how much storage do I need, how much compute do I need, try to predict that, and have that as an exercise. And then if you want to grow it, it's really, really hard to adjust that over time. What we like to recommend within AWS is actually decoupling those. Leveraging S3 as the storage of your data lake, and then leveraging the Hadoop and Spark on top of that, and connecting directly into the S3. It's interesting because Netflix actually has a blog post where they tested this configuration versus local HDFS on a Hadoop cluster. And they actually found some very, very consistent results, but interesting for people that are new to the cloud and Hadoop on the cloud, where the way you store your data and the way you write your analytics are going to far supersede the performance of an analytic than if it's on HDFS or S3. There's a slight difference. So if you look at their blog posts and their charts, their sequence files, when they're doing their queries might have taken 60 seconds versus 55 or 53 or whatever it is. But what's really interesting is if you just structure your data slightly different, that delta drops drastically. So if you use Parquet or RC or these other optimized forms, both the difference between sequence file on HDFS and Parquet on HDFS dropped drastically, but the difference between the Parquet on S3 and HDFS was less than a second. So the reason I like to mention this is, a lot of times if you're building this system and you're using S3 as a data lake, if a customer comes to me and says, I'm not really getting the performance I need out of it, the first thing I like to ask is, okay, one, are you running in the same region? Obviously, you would want your S3 bucket in the same region as your EMR cluster. If it's not, it's going cross-region. But the second question I like to ask is, what is your data format? Because if worst case scenario is like a gzipped CSV file that's not splittable, that is one, that would be like horrible, very, very performant if you architect it the right way. And this is exactly how Dow Jones is doing it, FINRA, a lot of our NASDAQ, a lot of our customers are doing this exact architecture with very, very high loads. And what this really buys you is not only being able to scale those independently, so you don't have to necessarily predict how much storage in your data lake you need up front. You could just consume it as you need it. But it also lets you set up multiple clusters. And this is important for a couple of reasons. The first is, when you're building this sort of architecture on premises, you don't really set up different clusters for different jobs, right? It's one big cluster with a resource negotiator that runs all these different jobs. And at times, if you look at the profiles, oftentimes there's a large queue during peak hours of the day, very, very low queue within Yarn, those sorts of things during other times of the day. What you could actually do is you could actually set up these dedicated clusters really, really easily. For example, if I have a job that needs to run every night, I could spin that up, point it to the same data on S3, point it to the same data catalog so it has the same logical view. So these clusters see the same data regardless of which cluster you go on with this architecture. But then you could spin up these transient clusters maybe to do an ETL job and leverage things like the spot market. Drive your costs down like 90% for these ETL jobs. And then you could have these interactive clusters, these streaming clusters that are very, very specialized that aren't necessarily competing resources for these other jobs to run. The other thing that this really lets you do is, let's say you have groups that want to be able to run different sorts of Hadoop jobs with different libraries. It's interesting because many times when you actually look at what libraries are needed for different versions of the analytical stack, sometimes not to pick on Avro, but maybe the Avro jar changed and it's not compatible anymore. I remember that I think one time for one Spark upgrade, or maybe these different jars don't really play nicely together. It's really, really easy to stand up another cluster, have your old jobs running on the old cluster, and do more of a blue-green deployment to the new cluster. And if you're doing this kind of in a traditional approach, you'd actually have to do a lot more data syncing, dist copies, that sort of thing, to be able to synchronize the data on the cluster. But you don't necessarily have to do that in this case because it's decoupled from that. I could probably spend about 2 hours talking about EMR and Hadoop systems. I won't do that to you guys. Don't want everyone leaving the room here. So let's kind of shift a little bit for data warehousing here. So data warehousing, really, really powerful within AWS. Amazon Redshift lets you, start with relatively small data warehouse clusters, so 160 gig warehouse cluster, and scale all the way up to the petabyte range. And what you could do is you could launch this cluster, you could shut it down, you can launch a new one, and it's fairly simple to actually plug in a very wide number of BI tools on here. And the reason why folks are doing this, and I should have said this in context of data lakes, is data lakes are really great for those analytics, for Hadoop, for machine learning, deep learning. You wouldn't necessarily have a business analyst talk directly to a data lake. You want them to talk to curated data sets that have been vetted. Maybe there's data biases in the data that you want to vet out, that sort of thing. Bless you. So, oftentimes what you'll have is you'll have your data lake populating these data warehouses. That could be very, very simple in terms of I have my data in S3, I have my data in Glue, my data catalog in Glue, and I'm just doing some copies into my Redshift cluster to be able to load that cluster. So you could start very, very small with this sort of architecture and grow as your needs grow. The other way of getting the data in here is using things like Glue ETL. So let's say in my data lake I have JSON data. JSON data is really, really great as a file-based data, but if you try to load JSON into like a normal relational database, not a document-oriented database, it's quite hard, right? It's very nested. It might have these different fields. What if you want to load some of that data into a data warehouse or a database? Let's talk about Redshift and data warehouse in this example. This is really where you might want to use something like Glue or some sort of ETL process rather than just a straight copy. Because what you could do is you can actually use functions called, there's one in Glue called relationalize. What that does is it will take a nested object, for example, a nested JSON or nested XML, and it will create a set of tables for you to populate it, your relational form. And these tables actually have the IDs referencing the parents and child. So if you have one object that actually has 3 children and then those children have more children, all the IDs match across the data frames or the dynamic frames that are going to be getting loaded into your relational store. So that's a really good method if you have kind of complex structures that you want to load into your data warehouse. Again, with data warehousing, it's schema on write. So with data warehousing, you define your schema up front, and you're actually writing into that schema. And that's why a lot of times people will park it in the lake first, and then pre-process it, transform it, load it into their data warehouse. So here's a nice long slide comparing some of the data warehousing versus data lakes. One of the key differences really is the second line there, schema on read versus schema on write. We talked about what that means, but when you apply that logical data model or physical data model, depending on what system it is. The other key thing I would mention is the use cases. A lot of times we're seeing, BI generally is powered by your warehousing, and then your data science, predictive analytics. There are some BI use cases that talk directly to a data lake. So QuickSight and Tableau both have Athena adapters, right? So you can technically set up a Tableau dashboard or a QuickSight dashboard to query directly into your lake. But if somebody came to me and said they wanted to do that, but they wanted to scale and have also very, very tight production SLAs, that's where the tipping point oftentimes is, where you might want to use more of a data warehouse or more of a Redshift. But how can we combine these a little bit more seamless? This is where Redshift Spectrum comes in. You wouldn't necessarily ever run Redshift Spectrum unless you're already running a Redshift data warehouse. Because Redshift Spectrum is actually a component of your Redshift cluster. It's actually a piece that's inside your Redshift cluster, and then there's a separate compute layer, which I'll show in a moment. But what it allows you to do is really combine both the schema on write and the schema on read together, or to say differently, your data warehouse and your data lake together. And what that means is, what I could do is I could actually define for my BI users or my users in my data warehouse a star schema, a certain schema that they're using to run their reporting on. But what I could do is, if I'm bringing in new data, or if I have a really a time-sensitive data load that I want to be able to access right away, NuViad is a really good example. They actually use Spectrum to be able to get the data to their BI users very quickly, where it's in seconds now instead of minutes. And what you're able to do is you're able to define these external schemas and point them to your data in your data lake. That might be a Glue S3 combination. It might be some other Hive store combination. It doesn't have to be Glue in this example. So you can have, as long as it's S3 in some sort of metadata store that's Hive compliant, you could actually configure your Redshift Spectrum external schemas to actually take some of the data out of S3 in your data lake and combine it with the data in your data warehouse. The time-sensitive example that NuViad does is one example of that. Another example is, maybe you have some really cold data, and then you have some really hot data, but you want both of those data sets exposed through the same tool to your BI users. So you might want, your BI users to be able to query data sets on the cluster, that hot data, and then for other sets of data sets to be able to query directly down to the data lake. And this is another really good example of where Redshift Spectrum gets used in this data flow. And the way this works when you're using Spectrum is the query still comes through that leader node. So Redshift is actually structured with a leader node, and then it has a set of compute nodes underneath it. And what happens is, as you're doing your querying, let's say I'm taking some of my hot data on my cluster. And let's say I'm taking that data set, I'm combining it with some cold data in my data lake, and I'm doing a join across those data sets. From the BI's perspective, or the BI user's perspective, all I'm doing is I'm querying two tables. One of them happens to be external schema or external table. So the user experience from the BI's perspective is very seamless, but under the covers, what happens is the external schemas through Redshift Spectrum gets delegated down to this Spectrum compute layer. That does a couple things. One, it actually offloads a lot of the compute. So anything that's done at the Spectrum layer actually isn't consuming compute out of your actual cluster. And then it's also then taking the data set, oftentimes doing like predicate pushdown, and bringing back as limited data set into the cluster as it can to be able to optimize that query. You could actually do things like create what's called late binding views. What that allows you to do is create a logical view across the data set, and that actually might join some data out of your hot data on your cluster and join it with the data on your data lake to create one view for those BI users. So some really good techniques to be able to leverage that data lake and that data warehouse technologies together to be able to provide those to those BI users. So, here what we're seeing, just as a higher level view is, taking that data out of the data lake, populating it both on the compute nodes of your Redshift cluster, but then also being able to query that data in place through things like Spectrum. One other thing, and the reason I want to add, expand on this a little bit, is you actually might have cases where data flows into your data warehouse first. It's not as common as flowing into S3. You know, even if it's flowing into your Redshift cluster, we like to have people state it in S3 and do copies anyway. But you actually might have data that's getting derived and generated within your warehouse and pushed back into your lake, maybe through a unload statement or something like that. But these are really kind of working together in conjunction with each other. So, you know, we talked a little bit about analytics, ingestion, metadata management, kind of completing the circle across that architecture we were looking at first is how do we start doing machine learning and deep learning on this big data set and really the data in our data lake. And why we like to talk about these things a lot of times together is machine learning and deep learning is all about driving patterns and recognizing things in data. You always end up plugging data into some sort of machine learning algorithm. It's all about being able to find what these functions are or these formulas are, and then being able to apply that to new data that you're seeing in the future. So we oftentimes like to talk about these flywheel effects. So as you get more and more data, you are able to make better decisions using a lot of the analytical-based tools. But then that's also driving better machine learning, better products, that sort of thing, which then drives additional data. So you know, we see this flywheel effect quite often, both on our retail side as well as working with customers. So on the machine learning side, you know, you guys have probably caught a common theme. It's all about being able to plug these tools into the lake here. And there's really these different classes of machine learning services. And it really kind of depends on what you need to get out of your data lake and what you need to get out of your algorithm. So if you're actually taking, let's say you're taking video information or you're taking imagery, and you want to be able to have that come in, but you also want to be able to make it searchable and drive insights and extract metadata, which then becomes part of your data lake itself. You might want to use something like one of our application services. These are services that allow you to not necessarily worry about the training portion. So you don't have to train on all these tags, all these different things. Maybe you have audio files that you want to transcribe, those sorts of use cases. What you could do is you could very easily set up various triggers in your lake to be able to automatically run, extract that information, and then store it back in there. The other thing that we see quite a bit is using things like SageMaker. So SageMaker is one of our platform services. SageMaker allows you to set this up so that when you're actually running your jobs, it connects into your data catalog. So we have lots of customers that are using Bodo and various integrations to Glue data catalog, and runs your jobs to be able to extract that information and get it out. One example I like to give is this Digital Globe example. So Digital Globe is a very, very large customer on AWS. They have over 100 petabytes in their data lake. They're very, very satellite data driven, but they run a lot of interesting analytics on it. So they work with various organizations to be able to identify fire movement whenever there's big fires or other natural disasters. So they're constantly taking this geospatial data, but also running advanced analytics and machine learning on the data. What's really interesting, though, is they actually used it in another use case that isn't kind of the traditional machine learning or deep learning example, where they wanted to really instead optimize operations. They wanted to be able to take that 100 petabyte data lake and be able to effectively cache that data to be able to set different bucket classes or different classes for their different objects in their satellite imagery. And what they're able to do, and there's a really good blog post about this, is they're able to use SageMaker and machine learning algorithms and change their storage classes on their data in their data lake to be able to drop their costs in half. And the way they did that is they predicted what data would be accessed. And as people were accessing the data, I have a really cool video here if it's going to play. So what we see here is the different cache hits over 3 months and which parts are being accessed. And they were able to predict with I think it was about a 90% accuracy of what data was going to be requested when. And when they're able to predict that well, they're able to set up their cache more effectively, have those caches smaller, move more stuff to cold storage that they needed to. And that's really how, through this architecture, they're able to drive those costs in half. So we have tons of really interesting examples on, satellite imagery, other types of videos, that sort of thing. I like to talk about this one because, it's kind of that operational use case. So we're really seeing this being applied throughout the ecosystem, not just, imagery, voice, that sort of thing. Another example here that we're going to talk about is FINRA and how they're doing machine learning on their data lake. They very, very rich system. FINRA actually developed their own metadata layer. They developed this before Glue Data Catalog came out. It's called Herd. So if you think of like herding your data, herding cats, it's an open source tool called Herd. And they're running all of that on AWS. They're using our services. They're using our partner services, things like Databricks, EMR together, that sort of thing. And what they're doing is they're taking all this stock information and running machine learning and deep learning on the data. And what their architecture consists of is, it's drawn slightly different because I think I stole this slide from one of their re-events or one of their summit presentations. But what you'll see is they actually have a very similar architecture, right? They have their storage, it's in S3. They have their metadata store, it's Hive compliant. They happen to be using Herd because Glue Data Catalog wasn't out yet in various reasons. They've been running this system for quite some time and improving on top of it. They're also running multiple clusters. You'll notice it's not just one Hadoop cluster. It's not just one Lambda. It's not just one compute layer. They're running different types of compute based on what type of job they're running on. What that really allows them to do through that architecture is not just use one tool here. So this is actually another screenshot of their, I think it's the Unified Data Science Platform is what that acronym stands for. It's something that FINRA calls their data science platform. And through this platform, they actually provide their scientists access to R and Shiny and Caffe and TensorFlow and scikit-learn and lots of these different tools, which is integrating with that catalog and talking to S3. And I didn't show the slide here. I don't know if it's on here. No, it's not on this one. They have a couple deep dive sessions on our previous re-events and summits talking about that data curation process, right? They're ingesting the raw data. A lot of times the market data coming from different firms calls different values different things. So they're storing all their raw data. They're creating the curated data sets. Those curated data sets are really driving the scientists' machine learning algorithms and driving those, both EMR jobs as well as the data that's getting provided to Databricks. So, if we actually take another view of this, this is another depiction. Down at the bottom, we have the real-time flow coming in, being able to run the analytics on the real-time processing, storing that data in S3 as that historic or that data posture over time, and then having the different tools to be able to provide that interactive and batch processing on top of it. So, last few kind of notes as core tenets and core takeaways here. The first is really data lakes and data warehouses are complementary. You might have a case where you want to use both, depending on what use case you have. Also, you could be very, very performant and still have the loose coupling of storage and compute. This is one of the things where, in my past life when I was building on-premises Hadoop clusters, going into it, I'd be like, aren't you going to lose performance? And the way you store your data is going to far supersede that. Try it out, optimize for the queries, and you'll get quite good performance out of that. We do have tools to be able to cache data on your cluster. There's something called S3 disk copy. I'd say less than 1% of the customers after they optimize would have to do something like that. There are ways of doing it just for those few outliers. Choosing the best job for best tool for the best job. So you're not picking one tool for ingestion, one tool for analytics. What we find is the types of analytics you run today is going to be very different from the types of analytics you might run 3 years from now, which is very different than what analytics existed 5 years ago. So you want a platform and you want this ecosystem to be able to evolve as your business questions change as well as the tooling changes under the covers. And capacity management, in big data and in data lakes, it's a really, really prime example of how the cloud could help with capacity management because it's all consumption-based if you architect it correctly. S3 is all consumption-based. When you spin up your compute, you're spinning it based on your compute needs. It's a really, really good example of that. And then the kind of last key takeaways, and I'll stick around here for questions and comments, but picking the right tool for the right data structure for what you want to do. Is it a data set that's constantly changing? For example, even in the curated data sets, Parquet is really good at some things, but maybe you want to use Avro or ORC or another format. So all your data doesn't have to be in your same format in your data lake. So think about, as you're looking at your data, what are the characteristics of the data? How much is it changing? What's the volumes? That sort of thing, as you're looking at the data structure. If I was working with a customer and they had like CSV data and JSON data, which are query-wise quite poor performing because they're very sequential, but if they're not dealing with large data sets, they're querying it once and then taking the data and sending it somewhere, they may not want to go through the process of optimizing it into Parquet or ORC. So just take a look at what the unique aspects of that are. And then, really the last thing I would say is, looking at your system, if you're costing it out, if there's a really giant cost for a lot of these systems, it's usually something that you want to engage the SAs, some of our team, to look at your architecture. Oftentimes we price our services to be optimized for how you want to use them. So if you try to take streaming data and store S3 where each record is an individual object in S3, it's not going to perform well because you're going to actually cost it out, and your put costs for S3 are going to be giant. Instead, you want to batch that data up, have a single put or a small number of puts out there, and that costing exercise is a really good validation on what the services are meant to do, that sort of thing. And definitely engage your SAs as you're going through that exercise. So, definitely want to thank everyone for attending. I'll stick around up here for questions. And thank you again.